In this video, I'd like to talk about the math question of the day for Friday, June 23rd, 2023. And with this problem, we need to consider this rational function, f of x, and determine this function's end behavior. Now, a topic like end behavior, specifically with rational functions, is typically taught in a pre-calculus class, though you will revisit this topic with limits in calculus. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through this. And with end behavior, we're concerned with what happens to this function as x gets bigger and bigger, or as x gets more and more negative. So we're wondering, as x approaches infinity, what happens to f of x? And as x approaches negative infinity, what happens to f of x? And with these rational functions, basically what we'll do is compare the highest power term in the numerator and the denominator. And that's mainly because as x gets bigger and bigger, these lower power terms, let's say we're focusing on the numerator, these lower power terms become less and less important. Let's say as an example that we plug in x is 10 to the 6th power, or x is 1 million, a 1 followed by 6 zeros. And when we plug it into this function, we're replacing x with 1 million, or 10 to the 6th. In our numerator, we would get 10 to the 6th to the 4th power, which is 10 to the 24th power, minus 4 multiplied by 10 to the 18th power, plus 6 times 10 to the 6th power. And we could do the same for the denominator, though the reasoning will be the same in the numerator and denominator. But basically, this 10 to the 24th, this is a 1 followed by 24 zeros. And then we're subtracting 4 followed by 18 zeros. And this number is so large that when we subtract this lower power term, this cubic term, this 4 followed by 18 zeros, it will barely change the number at all. It's like subtracting 4 from a million. It's still basically 1 million. Subtracting 4 from it doesn't really change the magnitude of that number. And similarly, when we add 6 followed by these 6 zeros, this is just 6 million, this will again barely change the number at all and will affect it even less. So as x gets bigger and bigger, this difference will be more pronounced. So as x approaches infinity, these lower power terms do not really contribute to what's happening to the function. The main term that tends to dominate the function is the highest power term. And it will be the exact same reasoning for the denominator. It will be this 4th power term that will dominate this denominator. So in essence, as x approaches infinity, this function will start to approach just the ratio of these highest power terms. The x to the 4th term divided by minus 5x to the 4th. And everything else will not really contribute as x gets bigger and bigger. And from here we can see that we can simplify this. Since this expression, we can cancel out x to the 4th in the numerator and denominator, we would just get 1 over minus 5. So as x approaches infinity, the function approaches minus 1/5. And we can also apply the same logic for when x approaches negative infinity. And since as x gets more and more negative, just like when it gets more and more positive, the lower power terms will matter less and less. And again, these highest power terms in our numerator and denominator will dominate the function. So again, we will really only need to consider this ratio here. As x approaches negative infinity, the function will start to approach the ratio of the highest power terms, x to the 4th over minus 5x to the 4th. And again, it will simplify to minus 1/5. So in both cases, as x gets either very large in the positive direction or very large in the negative direction, the function will approach this value of minus 1/5. Now, there is another way to approach this. We could take this rational function, and let me rewrite it, and I'll just write the expression, but we know that it's equal to f of x. We have x to the fourth minus 4x cubed plus 6x, and all of this is divided by minus 5x to the fourth plus 8x squared minus 3. We can manipulate this algebraically. And what we can do is multiply the top and the bottom by 1 over x to the fourth, or whatever the highest power term is in either of these. And we'll do the same in the bottom. We'll multiply by 1 over x to the fourth. And really, since we're multiplying the top and the bottom by the same number, we're multiplying the overall expression by 1, so we're not changing anything. And when we distribute, this just becomes a 1. We get minus 4 over x plus 6 over x to the third power. And for the denominator, we'll get minus 5 plus 8 over x squared minus 3 over x to the fourth. And as we let x approach either positive or negative infinity, these terms with x to some power in the denominator, all of these will approach 0. So if we think it through, basically we have a constant in the numerator and our denominator is getting bigger and bigger. It might be getting more and more negative if we're approaching negative infinity, but the main idea is that the numerator is fixed while the denominator is getting bigger and bigger. And the fraction overall would then get smaller and smaller. It will either approach 0 from the positive side or the negative side, depending if we're approaching positive or negative infinity, and if this is an even or an odd power. So likewise, these will also approach 0. And you can see that the function, again, will just approach 1 over negative 5, or minus 1/5. So this type of reasoning here is often used in calculus when dealing with limits. And with calculus, all we do is use a new notation. We say we're looking at the limit as x approaches, let's say, infinity of our function. And what we found is that as x gets bigger and bigger in our function, that this approaches minus 1/5. This is what we call the limit of the function as x approaches infinity. Now, one way that we can actually check this is by plotting this function on Desmos or some type of graphing calculator and actually looking at higher and higher x values or more and more negative x values. So let me quickly show you what this looks like on Desmos. And we can see that we have our function here, f of x, this rational function, and its graph right here. Now, if I zoom out, we can get a different picture of this. And we're looking at the end behavior. So we're looking at what happens as x gets really large. You can see the y value there on the right. And as x gets more and more negative. So what we can notice, let me zoom much further out, is that as x gets bigger and bigger, we can see this is approaching minus 0.2. And as x gets more and more negative, again, we can see this is approaching minus 0.2, but now we're coming in from the bottom. So in both cases, the graph helps us verify what we found algebraically.